Now, on to the homework. Questions on the problems that you did for today? Yep.
You do 10.
Number 10. Two small metallic spheres, each of mass 0.2 grams, are suspended from pendulums by strings of length L. Spheres are given the same electric charge, 7.2 nanocoulombs. They come to an equilibrium when the strings make an angle theta equals 5 degrees. How long are the strings? So we diagram out what we got here. .2 microcoulombs on each. Nanocoulombs, thank you. Let's see, we know the mass, 0.2 grams on each. We know an angle of 5 degrees right there. String has a length of L on both sides, and we know equilibrium. So net force equals 0. That would have to be on one of the objects. So if I draw the forces on one of the objects, weight mg, tension force there, electrostatic force of repulsion. Same diagram flipped over on the other one. Longer way and shorter way to be able to do this. Long way or short way? What are our options here? And I'll tell you if it's a long way or a short way. Sam, give me an option. What can we do?
Use the net force and have the what's it called? The tension force and like the horizontal component of the tension force and the electrostatic force.
Okay. So we can go components. And do here and do here. That's one way. That's another way. That's the long way. What's the shorter way than doing components?
Unit vectors.
It's still going to deal with components. What's a shorter way because we happen to have two of our forces that are at right angles to each other? What shorter way does that give us? That we've done before. Okay, what's going to be the sides of my triangle?
The electrostatic force and gravity.
If I draw these vectors head to tail, I'm going to get a right triangle. So I can go mg, electrostatic force, which form right angles, tension, takes me right back up there, and I get right back up there because I have equilibrium. I don't have any extra newtons. When you can do that, that's usually shorter than going down the component route. And we can do that because we have a right angle there. Okay, so then we want the length of the string. Well, let's see where this goes. We got 5 degrees is right there. Okay, if I go tangent of 5 degrees, electrostatic force over mg. So my electrostatic force is gonna be an mg tangent 5 degrees. Electrostatic force, that's a K Q1 Q2 over R squared is equal to mg tangent 5 degrees. You can plug in your numbers and solve for R. Once you solve for R, that's going to be this value. So then on my triangle here, if I extend this downward, this side is going to be half of R, this side is going to be 5 degrees. I want to know L. You can do a sine of theta to find L. Do I need to write out more? You can get to the same thing from doing components, but you're going to have to do a net force in the x equals 0, a net force in the y is equal to 0, and then bring them together to be able to solve down. And when you bring the two equations together, I bet you're going to get something with a tangent of 5 degrees in it. Okay? Either way works. Your right triangle is a little bit shorter. Anything else on 10? Next question. Yep.
13.
13. Three charged particles located at the corners of an equilateral triangle as shown. Diagram, calculate the total electric force on the 7 microcoulomb object. We had a 7, a 2, and a negative 4. Point 5 meters on each side. There. I'm going to call this charge 1 and this charge 2 because we're calculating the net force on the one at the top there. So if we draw a diagram of the forces first of all, okay, positive charge, negative charge, they're going to attract. So F2 will be right there. Positive charge, they will repel. F1 will be right there. 60 degrees there, so this will be 60 degrees, and this will be a straight line, okay? You could make the argument straight down, that would be 30, this is gonna be 60, and this is gonna be 60, okay? So then if we want the net force on the 7 microcoulomb object, each of our forces is going to be a K sub E Q1 Q2 over R squared. I'm going to factor some stuff out that's common. Okay, let's see. K sub E is going to be on everything. I'm going to pull that out. The 7 microcoulombs, that's going to be on everything. I'm going to pull that out. R squared, it's going to be the same R for everything. I'm going to pull all that out and leave the remaining charge and the vector stuff in. So then I got a 9 times 10 to the 9th. And the 7 times 10 to the negative 6 coulombs. And the 0.5 meters squared. Okay, now F1. It's got an X component and a Y component. The only thing left is the other charge, which is the 2 microcoulombs. So then 2 times 10 to the negative 6 coulombs cosine 60 degrees, tag it with an I. Same thing, but with a sine of 60 degrees. Tag it with a J. Let's see, the I, the J, they're both in positive directions. Okay, this one, same idea, but the Y component's going to be in a negative direction. So I got 4 times 10 to the negative 6 coulombs, cosine 60 degrees, tag it with an I, minus 4 times 10 to the negative 6 coulombs, sine 60, tag it with a J, crunch your numbers, combine your I's and your J's. I mean, pulling these out isn't necessarily going to save you much punching in your calculator, but it saves you a lot of writing of stuff. Next question. Anything else on these problems? All right, then we left off yesterday, pondering. Not yesterday, how about Friday? Pondering the electroscopes, aluminum leaf electroscopes. What did you do? What did you observe? What did you conclude? Going to make me call on somebody. No one's going to volunteer. Owen, call on somebody for me. What'd you do?
Well, I charged the balloon by friction and then held it up to like the metal ball part at the top of the electroscope.
Touching or not touching?
Not touching.
What did you observe?
That the leaves like would spread apart.
Okay, explain why they would spread apart. Is the balloon positive or negative? What are you assuming?
Positive.
Positive, okay. So if we assume the balloon is positive, then what happens in the electroscope when I bring the balloon near?
Well, if you charge the balloon by friction, you would have been like scraping electrons off of the balloon. So then it would have had, by the time you held just the positive charged protons up to the electroscope, they would have repelled from each other because there's also positively charged on the electroscope. That makes sense.
So how did the electroscope get positively charged? Because you didn't indicate you touched it.
Well, there would be a neutral charge then.
So it has no charge. So then why do the leaves repel when I bring the balloon near? How do the charges in the electroscope respond to the positive balloon?
It would attract to the others, or to the top of the electroscope through.
So what attracts? What charges in the electroscope attract to the positive balloon?
The charges from the balloon.
What charges in the electroscope attract to the positive balloon?
The negative charges.
Okay, can they get to the balloon?
Yes.
Okay, what's between the balloon and the electroscope?
Atoms.
Okay, of?
Oxygen. Air.
Air, conductor, and insulator.
Conductor.
Okay, so are you getting electrocuted because charges are being conducted from the outlets over to you? Nope. Air is an insulator. So that means the charges cannot transfer through the air to the balloon. but the balloon's positive. So what do the charges in the electroscope do? They're attracted, but they can't get there. Go ahead.
They're creating like regions of charge. So like the positive charges are like closer to the balloon. Like,
Why?
Or the electrons, the negative ones are because it's positive, so they're going to attract the negative ones.
So electrons within the electroscope are drawn up closer to the balloon, but then they can't go anywhere, so they get trapped there. So why do the leaves spread apart?
Because the other charges, the positive charges, are forced to go like further down, and then they kind of split in between the two aluminum leaves, and then since they're equal charges, they're going to repel each other, like the two metal leaves.
So what you're saying is mostly right, but we didn't have a nuclear explosion and die, so we have to amend a little bit. How do we amend? Seth, how do we amend what he said?
There's just electrons leaving the leaves, and so it's more positively charged now.
Right. It's just the electrons that are migrating up to be close to the balloon. The positive charges can't go anywhere. They're stuck in the nucleus. But because some of the electrons from the leaves have migrated up, there are less electrons down there. Thus, the leaves are positive. Thus, they repel each other. Okay? That's the level that you need to be able to think and explain through. And it doesn't matter if you assume the balloon was positive or negative. You could flip the signs of everything and still make the same explanation. If the balloon was negative, you'd be repelling electrons down into the leaves. They'd be negative, they'd still repel. So what happens if we touch the balloon to the electroscope? Sam, what happens when we touch? And I didn't neutralize it first, so we'll neutralize it first.
The same thing that happened before.
Same thing, but they stayed. Why do they stay?
Because it transfers
What transfers from where to where?
the electrons, the extra electrons on there transfers to there.
What was the charge of the balloon when we started? What do you want to make it?
We'll call it negative.
If the balloon is negative and I touch it, electrons go from where to where?
The balloon to the ball.
Balloon to the ball, and then I pull it away, but I didn't discharge it, so it may not be doing very well right now. So I pull it away, electrons have transferred, and I trap electrons there. Like charges repel. Other questions with the aluminum leaf electroscope? Miles, you look like you have a question.
I just don't really understand like what the electroscope is or how it works. I mean, is it just like all metal in there? Or?
Yeah, so, I mean, literally inside this metal rod, the ball, and then the metal rod, and then the white stuff is an insulator, okay? And then the metal rod continues down, and then metal little hooks, and then metal leaves. So, this white insulates it from the rest of the box, and other than that, the glass plate that is here just keeps it from wind or other things disturbing what's going on. Other questions? Why does the balloon stick to the cabinet door over there? What method? Yep.
Polarization.
Why is it polarization?
Because both the cabinet and the balloon are insulators, so they're not like going to be charging each other. Just the atoms are going to be shifting a little bit to face each other.
Just lopsiding the charges of the atoms in the cabinet door. Okay. Any questions on our methods of charging? Or recognizing what charges do and how they transfer? Electric fields. If we picture a charged object, so if I have an object here and it has a charge, and then I take another little charge, say a little test charge, and I move this test charge around here. What's my object going to do to that test charge? Parker, what's it going to do? Going to repel. We're positively charged, so it's going to repel it. So if I draw, you have a little electrostatic force of repulsion there. And really I could take this anywhere I want it around here, and anywhere I put it, it's going to repel. Okay, so then we can think of this region around my charged object, and I would need to go further, but you know, don't want to run my highlighter out of ink here, etc. Okay, we can think of that region around a charged object where that object, charged object, interacts with other charged objects as the electric field. And by interacts, we mean applies forces too. It's the same idea as a gravitational field. Region around Earth, where Earth applies gravitational forces to other objects of mass. Now, mathematically, we can think of this electric field, which we're going to abbreviate with a capital E. The stronger it is, the more force it's going to apply. So if we think in terms of newtons per coulomb, electrostatic force divided by the charge of the object. And if I bring my test charge back there, that would be the force on the charge divided by the charge of that charge at that location. Because you got two charges here. The central one that's causing the field and the one that's being placed in the field. You want the number of newtons of force acting on an object in the field. So this is the charge that is placed in the field. And this is the force on the charge placed in the field. If we pull Coulomb's law into this, remembering that electrostatic force is KQ1, Q2 over R squared, just like we did in problem 13 over there on the board. KQ1, Q2 over R squared over Q. Then the charge placed in the field is going to divide out. So we write it this way. This is the charge causing the field. These equations should look familiar, we used them last year. Units, newtons of force per coulomb of charge. And if we think of the equation in the second form, the KQ over R squared, this is similar form to your acceleration due to gravity equation. A sub g equals capital G mass of the body over R squared. It's the same idea, it's just a different kind of field. Electric field, far more important than electrostatic force. Okay. Let's consider an example. Electric field 1 centimeter away from a 1 microcoulomb object. Which equation are we gonna use? 50-50 shot. Look, second one, he saved you. Second equation, because we know the charge causing the field. You don't even need a calculator for this one, this is all powers of 10. Yes. And yet Patrick is still using his calculator. Got a value?
Yeah, I'm just trying to count the zeros. Put in the signs. 9E7 newtons per coulomb.
So 1 microcoulomb charge 1 centimeter away from it. Put 90 million newtons of force on a coulomb of charge. That's a heck of a lot. Yes, no? Just forgot my square down here. Yep. Because a coulomb of charge is a huge amount of charge. Okay? Expect to get big numbers for electric fields because it's a Newton per entire coulomb. And a coulomb is huge. We don't have anywhere near a coulomb of charge even causing this, but we get a huge field. Part B, distance that the field would be equivalent to gravity. Find out how far away you would have to be to have that field equal to gravity. Of course, gravity would be a Newton per kilogram instead of a Newton per coulomb, but equivalent in magnitude. Give me a number. Yep.
30.3 meters.
Agree, disagree? Got some agreement there. Okay, Q over R squared, so we're gonna plug in a 9.8 equal to 9 times 10 to the 9 times your Q, 1 times 10 to the negative 6 coulombs over R squared. 30.3 meters, that's like 100 feet away. Okay, to be able to get the field to be as weak as gravity is. Electrostatic fields are much stronger than gravitational fields. You are evidence of that right here as you sit here pondering. Because all your atoms are held together by basically these electric forces and these electric fields. If gravity was stronger, you wouldn't be sitting here. You'd be oozing here. You'd be oozing across the floor because gravity would compromise your chemical structure. Wouldn't be able to hold the molecules together. So the best you would be able to do would ooze. Okay? Gravitational constant times 10 to the negative 11th. Electrostatic constant, 9 billion. Electrostatic forces are far stronger than gravitational forces. Okay? Yes?
Why is a Coulomb so big? Like the practical applications of it, I mean, are mostly nano and micro coulombs.
Probably because we defined it before we knew how big the fundamental charge was. Okay? Before we knew that one electron only had a charge of 1.6 times 10 to the negative 19th coulombs. Before, who did the experiment to find the charge of an electron?
Coulomb.
No, Coulomb didn't do it. Rutherford did the scattering experiment to discover the nucleus. Who did the experiment to find the charge? Millikan. Millikan's oil drop experiment. You talked about that in chemistry last year?
I don't think so.
Millikan sprayed a fine mist of oil droplets into an electric field. Electrostatic force acting upward, gravitational force acting downward, balance them between the two fields. So then you basically had, if you multiply Q over, QE equals mg, and solve down for the amount of charge on the oil droplets. And then what did he do? He found the, factor, the common, smallest common, least common factor of all of the different oil droplets to deduce what the fundamental charge was. Okay, so that was all me going on a tangent. Now answering your question, okay, because we didn't know what this was when we came up with the unit. And so we defined a unit that is preposterously large. And then you know how scientists don't like change. Nobody was willing to change it. So it stays that way, basically. Okay? Other questions? Good question. Take a look at another example. Do part A, and then do part B if you're gonna do it the short way. Well, if you're gonna do it the long way, wait until we ponder it together. Electric field, you know you're looking for a big value. Usually 10 to the 5th, 10 to the 6th, 10 to the 7th. At least in that neighborhood somewhere usually.
Yeah, 1.13 times 10 to the 6th.
Direction?
I guess towards. Left.
Okay. Vector direction of an electric field. Standard notation is the direction a positive test charge would experience a force. So no matter what's there, you picture a positive. In this case, we have a positive, so then it would be to the left. Do we have agreement with 1.13 times 10 to the 6th? Do we have a different number? Okay, Q over R squared. Your Q should be the 5 microcoulombs, 5 times 10 to the negative 6 coulombs, plugging into there. Okay. Part B. Force experienced by the positive 8 microcoulombs. Okay, the long way is to plug into your force equation. The short way is to use the other form of the equation. E equals force over charge. So force is equal to Q times E. You just calculated E. Just multiply your other charge in there to be able to get the force. And you can figure out a value for that. Part C, find location or co-locations where the total electric field due to the two charges will be 0. You need to consider everywhere. Somewhere over here, I'm going to call this location 1. Somewhere between, I'm going to call that location 2. Somewhere on this side, I'm going to call location 3. Somewhere up here above, I'm going to call location 4. Somewhere down here, I'm going to call location 5. You got 5 different regions. What region or regions could we possibly get 0 field? And explain your thinking. Lauren, what are you thinking? 1, 2, 3, 4, 5. Where could we get 0 field?
I was thinking like region 2 because you could have the electric field from the positive 8 canceled out by the charge from the negative 5.
Okay, so if I picture a little positive test charge in here somewhere, what direction would the 8 put a force on it?
To the left.
So we'd have a force from the 8 in this direction. What direction would the negative 5 put a force on it?
Also to the left.
Those are going to have to cancel each other out? No. So this is what you do. Draw your little positive test charge. Check your arrows, and then check your reasoning. Can they be equal, or is one of them always a winner? Or a loser, depending on how you want to think about it. So we've knocked out region 2. 1, 3, 4, 5. Where could we get a 0? Seth, what are you thinking?
Maybe 1.
Okay, explain.
It's like it has a longer R from the higher charge 8 microcoulomb one, which would repel it to the left, and then the negative 5 microcoulombs would attract it, but slightly less, or even to the repellent force, I guess, or repulsive force.
Attract or repel?
Attract.
Yeah. So they are in opposite directions. Okay? And the 8 is always, 8 is a bigger charge, but it's at a bigger R. 5 is a smaller charge, so a smaller force, but it's at a smaller R. Yeah, this is a possibility. Is region 3 a possibility? Julia, are you yawning? You should get all charged up about these problems. Is region 3 a possibility?
I'll say no, because like the 8 microcoulomb charge is like just bigger on that side.
8's gonna repel, 5's gonna attract, but 8's always bigger than 5. So that's not gonna be a possibility, and that's not a possibility. What about regions 4 and 5? We draw a little positive test charge here. Attracts to the 5. Repels from the 8. We're going to be able to get a 0? No. Okay, so if you're just looking at this, no, do this. Draw. And you'll be able to eliminate both 4 and 5. Okay? That's how you decide. So now we know we're over here. So now we want a region, or we want a location where the field is equal to 0. My field is going to be in the same direction as the force. Sometimes it's easier to think of the forces. So we want the field from the 8 combined with the field from the 5 to give me a 0. K sub E, Q over R squared, so this is going to be K sub E, 8 microcoulombs. Oh, we got to figure out how to deal with R. K sub E, 5 microcoulombs. How do we deal with R? I need the distance to the 8 and the distance to the 5. Here's the distance to the 8. There's the distance to the 5. How do I represent those? Yep.
Like R and R plus 0.2.
Sure. R for this one, this is 20 centimeters. R plus 0.2 meters for that one. Okay, so then we are an R plus 0.2 squared and R squared here. Lots of stuff divides out. We get 8 over R plus 0.2 squared equals 5 over R squared. Yeah, we're not going to crunch through all the algebra. How are we going to solve that down, though? What are we going to end up using to solve that down? Quadratic formula. Yeah, so you have to square that, get all your r's and everything on one side, and you end up using quadratic formula. Quadratic formula is going to give you two answers because you have a plus or minus in there. One of them is going to be the one we want. One of them is going to be here. Where's the other one? Where else can the two forces be equal to each other? But not put it in equilibrium. Parker's shaking his head. He's like, nowhere. Did I read your mind or not read your mind?
I don't know.
I'm getting good at this. Where else can the two forces be equal but not put the charge in equilibrium?
Somewhere between them.
Yep. They can be equal here, but they're both in the same direction. So you will get two answers, but you have to decide, this is the one I need, and this is not. It's equal forces, but it's not an equilibrium, yes.
Could you solve the algebra instead by taking like the square root both sides to like get rid of the square?
You'll eliminate one of the roots. 50-50 shot, whether you eliminate the one you need or not the one you need. Okay? So yeah, square root, yeah, that's not gonna do it because you'll lose a root. Questions? Just wait for derivations tomorrow. The fun stuff begins. All right, we'll stop there. Perfect timing.